Our next speaker is Prein, also from the Max Planck Institute for Evolutionary Anthropology in Leipzig, Germany.
Okay, can you all hear me? No. All right. Like this, is it better? Okay, perfect. Okay, thanks for the introduction. So my name is Julia, and today I want to talk to you about the development of gaze understanding across 6 communities. So why are we interested in gaze? Children use gaze cues to adjust their focus to relevant environmental features. So gaze is important for more sophisticated social cognitive abilities as well. For example, if you want to judge what an agent can or cannot know. This is also an essential ability for building common ground in shared activities and also then supporting cooperation. In addition, as we've already learned a bit in the morning, gaze and language seem to be related. For example, gaze facilitates word learning by helping to identify the referent of a new word. Here we can see a traditional gaze following paradigm. So research so far often studied eye and head movement together. Children are then often presented with a dichotomous object choice, and analyses traditionally focus on the earliest age when children reach an above chance performance. So while the emergence of gaze following has been well established, less is known about the developmental trajectory throughout childhood and adolescence. And also, we don't know that much about where children actually differ from one another. So with our study here, we aim to address these points. We use subtle gaze cues without head orientation and a continuous measure to study the differentiation of this social cognitive ability. We focus on whether children understand the communicative intent of gaze. So we assess whether children localize an agent's attentional focus, but then also go one step further to use this information to guide their own behavior. That's why we call this concept gaze understanding. We strive to embrace and explain diversity in gaze understanding and focus on variation between children. The focus on individual differences leads us to 3 main questions. So first, how does gaze understanding develop? Then, what is the process behind it? And which factors influence the development? To study individual differences in gaze understanding in children and adults, I implemented a new task. You can find all the relevant details in this preprint. The task is online and ready for use. So let's have a look at the task design. So we asked participants to locate a balloon. You can see an agent and a balloon in the center. The balloon then falls to the ground and participants have to find it. For this, they have to use the agent's gaze as a cue. Our task uses a continuous spatial layout. Our dependent variable is the distance between the actual target's position, so that is where the agent looks to, and the child's click. Participants complete 15 test trials within 5 to 10 minutes, so it's rather quick data collection. And even though here you can see a computer mouse, we use tablet for data collection so that the children can touch the screen directly. To scale up data collection, I also implemented a new testing infrastructure. So our study gets presented as a website that works across devices and runs on any browser. Data can be collected in person or remotely. As a first effort, I collected data in Leipzig, Germany, and online. In the Institute in Leipzig, we have an extensive database of families. We can easily collect contextual variables via parental questionnaires, and children are used to participating in our studies. This makes it a great place to collect big sample sizes and study individual differences. However, it's important to remember that Leipzig is not exactly representative of the world population, as my colleagues Roman and also Marlene already mentioned earlier. So children in Leipzig are often raised in nuclear 2-generational households with few household members. The plot here shows household composition across the world. The darker the color, the greater the household size. You can see Germany is actually very much an outlier. Similarly, most children in Leipzig are experienced with touchscreens, which might not be exactly the status quo around the globe. These are 2 factors that might influence an individual's performance in our task: the amount of experience with social and technological input. We will keep these 2 dimensions in mind. Let's first look whether we find any individual differences in gaze understanding in Leipzig children. So here on the x-axis we have age on a continuous scale, and the y-axis shows a child's mean imprecision. That is the absolute distance between the target and the participant's click. So smaller values mean less distance, so greater accuracy. What we can see here is a lot of variation. Some 3-year-olds are more accurate than some 5-year-olds. Also, there are no ceiling or floor effects. And we do see developmental trajectory that the older the children get in general, the more accurate they are. So we see individual differences, but also development. Now we ask ourselves whether this is genuine individual variation or rather random noise. That's why we check the consistency of our measure. Internal consistency and retest reliability show that our task measures children's and adults' abilities reliably on an individual level. Now that we find reliable individual differences, how can we actually interpret them? What is the process behind it? To answer this question, we formalize the understanding of gaze cues in a computational cognitive model. So we ask ourselves, how do children actually solve the balloon finding task? We think that participants estimate the agent's eye center and the location of the pupil center. With this information, they can estimate an angle, or if you want to think about it a bit differently, a gaze vector. Extending this vector as a line then points towards the attentional focus of the agent. For every trial, participants then sample from a distribution of gaze vectors. The width of the gray lines represents the level of uncertainty. So where do individual differences come into play now? We assume that people vary in their deviation, so how wide the distribution around the true gaze vector is. Here we see an individual with more uncertainty. They should show greater click imprecision. So individuals differ in how accurately they estimate this gaze vector. The whole geometry of the situation also leads to interesting group level predictions. So let's stick to our more precise subject A here. So here we see what happens when the agent focuses onto a point in the center. What happens when the agent looks to the very left or very right now? So as the pupil location varies, a fixed amount of uncertainty about the eye angle corresponds to a varying amount of uncertainty in the estimated target position. This is something that we call headlight distribution. It leads the model to predict that our trials vary in difficulty. So participants' clicks should be more imprecise the less central the target x-coordinate is. This produces something that we call gaze funnel. So do we actually see this pattern in our data as well? The very short answer is yes. Let's have a look at it. So our x-axis here represents where the balloon landed. So to the very left, to the center, to the very right. Our y-axis, again, represents the imprecision as the click distance from the target. So here you see that children are more precise when the balloon lands closer towards the center. This shows that we can use our model to make interesting predictions. The model also allows us to disentangle where people's errors come from. So for now, we assume that children use the gaze cue. But there might be alternative strategies. Children's clicks could also be generated by guessing. In this case, we further subdivide. Children could click randomly. This would mean that they click on every location equally often across the trials, or they could show a center bias, so they could always click towards the middle of the screen. So our modeling framework now allows us to estimate the proportion of data that is best explained by either model. Let's see what this looks like for our Leipzig children. So here we see that the behavior of our 3-year-olds is most often explained by guessing. Some engage in random guessing, while the biggest proportion is due to the center bias. The older the children get, the more the model assumes them to make use of the gaze cue. Now this shows us a big advantage of our model. We can find answers to the question of what kind of errors children make and what strategies they use. For now, we saw that our task reliably captures individual differences in gaze understanding and that our cognitive model can explain these differences. So far, we relied on a Leipzig sample. Now we wanted to extend our scope and see how different social environmental factors influence the development of gaze understanding and how generalizable our model is. Therefore, we started working cross-culturally. Even though I'm the one standing here talking to you, this project is a hugely collaborative effort. The cross-cultural work is still ongoing, and I will present preliminary results now. So we collected a convenience sample. However, the communities vary in relevant dimensions that could impact children's understanding of gaze. For example, social environmental input and exposure to technological devices. We worked with communities in the global north and south, in urban and rural contexts with varying degrees of market integration. For contextual adaptations, local research assistants translated the audio prompts and decided on agents that were modeled after the local population and appearance. Before I present you our preliminary results, some words on our approach. So we expect parallel developmental trajectories across communities. We do not aim to rank communities according to performance. Rather, we investigate the influence of these social environmental predictors on relative imprecision within culture. Let's first look at whether we find the same pattern expected by our cognitive model across communities. Yes, we do find it. So the further out the target lens, the less accurate children are. This supports our hypothesis that we see a similar process across communities for how children solve the task. Let's remind ourselves about the variation of children in the Leipzig sample. Based on our reliability estimates, we know that we capture genuine variability, not just random noise. So this is now how variation across the sample looks like. So data from all communities vary between individuals, and we don't see clear clusters. Now, can we see developmental trajectory within community? So we see very similar developmental trajectories across the communities, but it looks a bit messy, right? The distributions across communities overlap wildly. We do not have a clear clustering by community. So gaze understanding looks rather cross-culturally constant. However, there is so much variation that the slopes don't do justice to individual children. Here, for example, we see two individuals from the same community with similar age that show very different levels of imprecision. You see, it's difficult to explain the data on a group level. And we do not want to reduce children to their group membership. So an explanatory approach seems more sensible on an individual level. Now, let's have a look at where the variation might be coming from. Factors might be testing infrastructure and family settings. Let's first have a look at exposure to technological devices. So here we see a so-called technology index, which we might use as a very rough proxy for exposure to technology. You see that there is some variation across the countries that we studied. But more specifically, how does it look in our own sample? In our study, we asked families whether their child has experience with touchscreens or not. We found quite some variation in touchscreen exposure. So how does this influence the imprecision in our tasks? So in the plot here on the right-hand side, you see the distributions of model estimates that predict imprecision, meaning the more negative the value, the more accurate. And we find an effect pointing into the expected direction. When children were exposed to touchscreens, they were more likely to respond more accurately. And this holds across the communities. Another influencing factor for children's performance in our gaze understanding task might be social input. Household size might be a very rough proxy again. Again, we see quite some variation worldwide. How do the countries in our own sample compare now? So we already saw Germany being quite an outlier. The other three countries where we collected data in show different household compositions and greater household sizes in average. Do we see the same pattern in our own data? Yes. Our Leipzig sample is an outlier. Families often live in two-generational nuclear families. Stanford shows similar numbers, while the other communities report greater household sizes. Let's see how household size influences gaze understanding. Again, we see estimates from our posterior distributions. Here we see very weak effects that mostly go into the expected direction. The bigger the relative household size, that is scaled within community, the more accurate children use the gaze cue. I think it's surprising that we find this tendency at all. We have a rather basic fundamental social cognitive ability on the one hand side and a rather far away real life variable on the other. So once again, this is a snapshot of our cross-cultural data so far, and it's very much still ongoing, so results can still change. What do we want to do next now? First, we're collecting more data in rural and urban communities worldwide to capture even more diversity and variation. In addition, we will use and extend our computational cognitive model to model the influences of cultural and social environmental variables. Now, combining cross-cultural work and computational modeling allows us to explore a child individual's behavior in context and in greater detail. With this, I want to thank all of these collaborators, all the families that participate in our study, and thank you for listening.
Thank you, Julia, for the amazing talk. Time for questions. There's a question in the back we'll take.
Very, very interesting work. I don't know if you're familiar with Stuart Anstis' work in the 1970s. So he used the ping pong balls to establish what you found here, just the location affects the accuracy. But the underlying computation involves two eyes, as well as the sclera and the iris proportions. And we also done studies with adults. We showed distance also matters, like where you look. So in order to basically dissociate between technology use and the actual development trajectory, I think probably you need to change the location. Instead of doing the tuning function on the same plane, you have to do something back and forth. So I think that would help you. And also you can change the sclera color, like the contrast is higher, accuracy is higher. So if you do that, then you can rule out the technological use on your effects.
Thanks a lot for your comment. I think that's a very good point. We actually thought about a lot of different versions of this task that we could still do. And I think varying the position of the agent is a very relevant one. And I think that would be super interesting. Also maybe varying on where the target is at the end. We could also imagine something like doing a clock, right, where the target could actually land everywhere on like all the different dimensions. But I also think like varying the distance could matter a lot. For the eye colors, I think that's also interesting. So we didn't check that exactly, but we did compare the different phases in our paradigm, and we didn't see any difference between the different agent stimuli that we used. But yeah, I could also look into that a bit more in detail. Yeah, thanks.
There was a question in the front.
Thank you for your talk. It's more of a clarification question. So I'm assuming you're studying typically developing children?
Say that again?
I'm assuming you're studying typically developing children. And I was just wondering, in the global south, like in rural communities, can you actually tell, like, are the diagnosis systems developed enough? Can you make sure that in your samples there are no kids on ASD spectrum? Or how do you deal with it?
That's a very good and tough question, and to be honest, that's not my area of expertise at all. I honestly couldn't tell you. Yeah, maybe it would be good to talk to our cross-cultural colleagues. Yeah.
There's time for one more question. Yeah.
Thank you for your talk. I was curious whether the motivation behind disentangling the joint head and gaze cues and just looking at the gaze cues was a sensitivity question, or is there also a broader thing that you're investigating about whether there are conceptual, interactive, or communicative differences between people who fully engage in like a very ostensive act of moving their whole entire head and their gaze versus someone who's very fixated and just moves the gaze?
Yeah, that's a very good point. I think also a discussion that we had in our department already a bit, like how relevant are these small, subtle stimuli that we use actually. And I think for us it was, the decision was based on sensitivity and also our goal to find individual differences. And I think if you actually have very clear ostensive signals and a lot of pointing and head rotations and talking to the children and so on in an dichotomous object choice, then it's rather hard to find individual differences, especially when the children grow older. So I think the more subtle the cues are, the more variation we can find. So that was rather the underlying motivation behind this. Yeah.
Okay, thank you. Let's thank our speaker.